Hi everyone. In this video we're going to talk about orthogonality and orthogonal sets and orthogonal complements of subspaces and all sorts of fun stuff, and this will allow us to push into the solution to the least squares problem, which I'm sure that we're all excited about. So to begin, let's recall, of course. The main instrument that we're going to use in orthogonality, of course, is the dot product. The dot product of two vectors, u and v, in Rn is u dot v equals. Well, let's define u. Suppose that u is the vector u1 all the way down to un, and v is the vector v1 all the way down to vn. Then we know that the dot product is going to be u1 v1 plus all the way down un vn. But now that we love matrices and matrix multiplication, we can actually write this as v transpose times u. And I swapped the order for strange reasons, but v transpose times u. What's v transpose? Let's see that these two things are the same. V transpose times u is, well, it's this thing transpose, so it's the row v1 through vn times the column u1 through un. And whenever we do the multiplication, we indeed get v1 u1 plus all the way down to vn un. Yeah? And this is technically a 1 by 1 matrix. Yeah? And this is technically a scalar, but we know that we can identify these two quantities in the obvious way. Let's recall a couple of fun, easy properties of the dot product. We know that the magnitude of v can be given by the square root of v dot v, right? And we also know that v plus w, quantity squared, well, maybe not square, is less than or equal to the magnitude of v plus the magnitude of w. And this is called the triangle inequality, if you remember. Yeah? Alright, so let's define, and there are lots of other properties. You might want to brush up on your knowledge of the dot product if you've forgotten things. So let's define an orthogonal complement. Definition. Let W be a subspace of Rn. Then we're going to define the set W, and this is like an upside down capital T here. It's like the perpendicular sign that you remember in geometry. We read this either, I usually call it W perp, or the orthogonal complement. Yeah? So we can define W perp as the set of all vectors z in Rn such that z dot w is equal to 0 for all w in the subspace big W. So what is W perp, or the orthogonal complement of W? It's the set of all vectors such that, what does it mean if z dot w is equal to 0? It means that they're orthogonal, right? They're perpendicular. So it's a set of all vectors perpendicular to every vector in W. Okay? So let's do a quick example. Let W be equal to the span of the vector -1, 2, 5. Find a basis for W perp. You might want to pause the video, see if you can figure this out yourself. You have all the tools, there's nothing new here. So try to do this yourself. Alright, so let's let z be some vector, z1, z2, z3, And suppose that this is an element of W perp. What does it mean if it's an element of W perp? We know that it must be perpendicular to every vector in the span here, right? Well, what does that mean? That means that Z has to be perpendicular to certainly every basis vector. So that means that Z dot, the only basis vector for the subspace, is this vector, and that has to be 0, right? And indeed, what do we want to do? We want to find a basis for the set of all Z such that Z dot, that direction vector, -1, 2, 5, is 0. Well, let's write out what this means. This means that -Z1 plus 2Z2 plus 5Z3 is 0. Sorry about my handwriting here, right? So how do we find a basis for all vectors that satisfy this equation? We can recognize that this is really a system of equations with one equation and 3 unknowns, and we're really trying to solve. So let's do that. We're also finding kind of the null space of a certain matrix as well. If you recognize this as the null space of a certain matrix, namely the matrix is -1, 2, 5 as a row. And so what do? We want to solve. Let's take -1, 2, 5. There's our row. Augment 0. And we want to row reduce. And congratulations, we're now done, right? So we have 2 free variables, 1 basic variable. So we know that Z3 is equal to S. That's an S, sorry. Let Z2 be equal to T. And Z1 is, of course, 2T plus 5S. And so what do we have? We have that my vectors, Z1, Z2, Z3, that live in W perp, have to really be, well, it's a vector times T plus a vector times S, right? How many T's are there? I see 2, 1, and then 0 of them. How many S's? I see 5, 0, 1. So what's a basis for W perp? A basis for W perp is just formed by the set of this vector and containing that vector. So if you have a set containing those 2 vectors, you have a basis for W perp. Because again, it's the null space of this nice, easy matrix. Okay. All right. Let's do an example. And this is a good review of your subspace knowledge. Show that W perp is a subspace of Rn. Yeah. You have all the tools that you need for this. Pause the video, see if you can give this a shot yourself. Alright, so let's recall. We need to show that W perp contains the 0 vector. We need to show that it's closed under addition and scalar multiplication. So, let's show that W is an element of W perp. Well, how do we do this? Clearly, 0.W is equal to W for all vectors W in the subspace W. Yeah? So we must have that 0 is an element of W perp. Yeah? Because it's certainly included in the elements of things where if you dot it with W, any element of W, you get back the number 0. 2. Let's let V and W be 2 vectors in W perp. Yeah? And let's pick some other vector Z that lives in W. We know if V is in W perp, what does that mean? That means that V dot Z is equal to W. W in W perp means that W dot Z is equal to 0. What do we really want to show, though? We want to show that V plus W is in W perp. So let's dot it with Z. Well, we know that dot product is distributive over addition, so this is equal to V dot Z plus W dot Z. And because V and W are both in W perp, we know that this is 0 plus 0, which is 0. So we do have closure under addition. Closure under scalar multiplication follows similarly. Let's let C be a scalar. And we'll pick V and Z that we've already used. We know that V dot Z is equal to 0. We really want to see, though, haha, funny pun, if C times V is in W perp. So what do? We take C times V and we dot it with Z. Well, we can pull out scalar multiplications and dot product. V dot Z is 0 because V is in W perp. So we have C times the number 0, which is 0. So we have closure under scalar multiplication. So this is a subspace. Yeah? All right. So we know what it means for two vectors to be orthogonal. Right? Two vectors are orthogonal if their dot product is 0. Let's define something related. A set of vectors v1 through vp, and this set will live in Rn, yeah, is an orthogonal set if vi dot vj is equal to 0 for any pair of indices that are not equal, for any I and j that are not the same. So what does this mean? That means that if you pick any pair of vectors in the set, any distinct pair of vectors in the set, their dot product must be 0. So they're pairwise orthogonal is what we say. Let's do an example. Let's let v1 be the vector 3, 1, 1. That's a 3. Let's let v2 be the vector negative 1, 2, 1. Let's let v3 be the vector negative 1 half, negative 2, 7 halves. Question. Is the set v1, v2, v3 an orthogonal set? Yeah? Pause the video, see if you can figure this out yourself. So let's compute the pairwise dot products. What's v1 dot v2? Well, v1 dot v2 looks like negative 3 plus 2 plus 1, which is 0. We're on a good track, right? What's v1 dot v3? It's negative 3 halves minus 2, so negative 7 halves, plus 7 halves, which is 0. And then what is v2 dot v3? It's 1 half minus 4 plus 7 halves, so that's 8 halves minus 4, which is again 0. So the answer here is yes, this is an orthogonal set. Why do we only need to consider 3? All the other pairs are just going to be these, but with the order reversed. And we know that the dot product with real numbers is commutative, so we only have to do these 3. Yeah? All right. Theorem. And this one's super nice. I think this is also a homework question, or a test question maybe, I don't remember. Let v1 through vp be an orthogonal set of non-zero vectors. Living in Rn. Then S is linearly independent, is a linearly independent set. Yeah? Pause the video. This is a really good practice problem. Pause the video, see if you can figure this out yourself. All right, let's prove this. Well, we want to show that this set is linearly independent, so let's start off with a linear combination, C1V1 plus all the way down to CPVP. Yeah? And let's set this equal to 0. And we want to show that C1 through CP must be necessarily 0. Well, at this point, let's use the fact that these are all orthogonal. Yeah? How do we do that? What happens if we dot both sides with the vector v1? Well, let's do it. If I dot both sides with the vector v1, the left-hand side I get c1 times v1 dot v1 plus c2 times v1 dot v2 plus blah 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 plus cp times v1 dot vp equals, what is 0 dot v? Well, that's just going to be 0, right? Yeah. And again, this is the vector 0 because it's a linear combination of these vectors, yeah? So there's no problem here. All right, so what do we know? We know that this is an orthogonal set. So what's v1 dot v2? It's 0, right? And all the way down, v1 dot vp is also 0. So we're left with c1 times the magnitude of v1 squared is equal to 0. Because v1 dot v1 is the magnitude squared. I know that v1 is non-zero, so that means necessarily that c1 has to be 0. Yeah? And now there was nothing special about dotting both sides with v1. We could have done this with v2, v3, all the way through vp. And so doing this for all vectors v1 through vp, we see that c sub I will be 0 for all values I from 1 up to p. Yeah? Because again, there was nothing special about doing this with v1. All right. Definition. An orthogonal basis for a subspace W is a basis that's orthogonal. That's hopefully not surprising. So we have a basis of W. If we have a basis of W that happens to be an orthogonal set, we say that it is an orthogonal basis. A related definition is an orthonormal basis, and these are super nice. Well, let's define an orthonormal set. An orthonormal set is a set of vectors v1 through vp that is an orthogonal set and every vector is normalized. What does that mean? That means that all of them have magnitude 1. So the magnitude of all of the vectors in your set is equal to 1. That's an orthonormal set. So the big kahuna, the one that we're after, is an orthonormal basis. An orthonormal basis, and we even have a symbol for this. Most of the time you'll just see ONB for an orthonormal basis, and this is used for subspace W is a basis of W. That is an orthonormal set. Yeah? And I know what you're thinking. Who cares, right? Remember our idea in linear algebra, a lot of our ideas go back to tiling the plane or tiling your favorite subspaces, right? Well, whenever you learn trigonometry and you learn vectors, how did we decompose vectors? A, B, back in trigonometry, or whenever you saw this first. We decomposed it in terms of A times I hat plus B times J hat, right? And these I hats and J hats were special vectors in R2. I hat's here, J hat's here. What do we know about the length of I hat? It's 1, right? What do we know about the length of J hat? It's 1. What do we know about the angle between I hat and j hat? It's pi over 2. So these, and indeed, if you dot them, you get 0. So this is an orthogonal set. So it turns out the set of vectors, I hat and j hat, is our prototype that you should think in your mind of what an orthonormal basis is. It allows you to form nice, easy coordinates. Yeah? And each of the basis vectors points in kind of its own direction. Remember, we were kind of frustrated. Let me draw another little picture here. We were frustrated because we know that a perfectly good basis could be this vector and this vector. But we know that in some sense they're kind of overcounting the same information. What's nice about an orthonormal basis is that they both have length 1, that's super nice. But the fact that they're orthogonal means that I hat contains absolutely no information about j hat, right? The coordinate a comma b, right? A is the amount that the vector moves in the purely I hat direction and gives no information about how much it's moved in the j hat direction. And then B gives information only about how far it's moved in the j hat direction. So having things be nice and orthogonal allow us to cleanly understand the geometry of the space that we're thinking about. Yeah. All right. Let's talk about a theorem. And let's see, how do I want to write this? We'll do m by n. An m by n matrix U, that's a capital U here, has orthonormal columns if and only if U transpose times U is the identity matrix. Let's prove this. If it's square, it's going to have a special name. It will be called an orthogonal matrix. And if you allow complex numbers, they're typically called unitary matrices, which is why they're typically symbolized with U, yeah, or denoted with U's. So proof, let U be a matrix. And suppose we have columns U1, U2, subscript 2, all the way down to UN. Yeah? And let's compute now. We'll put it here, U transpose times U. Well, how do we write U transpose? Again, these are a bunch of column vectors, right? What's U transpose? You swap the rows and columns. So the columns of this matrix need to become rows, and we'll do that with the transpose. So it becomes a column vector. U transpose is a column with rows given by U1 transpose, U2 transpose, all the way down to UN transpose. And now let's multiply it by U. And let's see what we get here. I know that for the 1, 1 entry, I'm going to multiply the first row of U transpose by the first column of U. And what is this? So it's U1 transpose times U1 for this entry. In the first row, second column, I multiply the first row by the second column, and we get U1 transpose times U2. And you continue all the way down until you hit U1 transpose times UN. What's in the second row, first column is the second row times the first column. So that's U2 transpose times U1, all the way down to, let me make my matrix bigger, sorry, UN transpose U1. And this goes all the way across to UN transpose UN. So you can fill up the entire matrix here. So let's see what's happening. Well, and we'll do the if and only if. It's kind of immediate at this point. If this is equal, or well, if they're orthonormal, okay, if each of the columns here, U1 through UN, form an orthonormal set, yeah? What's U1 transpose times U1? Well, they're normalized, so they all have length 1, right? And this is equal to the magnitude squared. So what's the magnitude squared? It has to be 1. What's U1 transpose times U2? That's U1 dot U2, right? Well, what's the dot product if they're orthogonal? It's 0. And that's true for that entire column here. U2 dot U1 is also 0, and all the other entries are 0. The 2, 2 entry will be U2 transpose times U2, which is 1 because that's the magnitude. And we see that the identity matrix will form. If we wanted to go the backward direction, suppose that this equality is already true. If we have all the dot products are 0 except whenever you have the dot product of a vector with itself, which is 1, that's exactly what it means to have orthonormal columns. So both directions are true here. All right, let's get a definition. An orthogonal matrix, so we mentioned that this is our special name for these things, is a square, so it has to be square, invertible matrix such that U transpose U is equal to the identity matrix. Yeah? So it's really interesting that these orthogonal matrices, if they're square, yeah, so if an orthogonal matrix satisfies U transpose U as the identity, so the inverse of U is just U transpose. That's kind of interesting, right? All right. Who cares though, right? These orthogonal matrices have really, really nice properties. Theorem. Let U. We won't make it orthogonal. We'll just let it have orthonormal columns. Let U be an m by n matrix with orthonormal columns. And suppose we have two vectors x and y in Rn. Then 1. The length of ux is equal to the length of x. What does this mean? If you take a matrix with orthonormal columns and you multiply it by a vector, you do not change its length. So all that it could potentially do is like rotate and things, right? But you don't change the length. It's called isometric. Ux dot uy is equal to x dot y. 3. Ux dot uy equals 0 if and only if x is equal to x dot y. Yeah. So essentially, U plays no role whenever you do with multiplication by U, plays no role in the length. It plays no role in the angle between vectors. Yeah? And it plays no role in orthogonality. So that's really interesting that applying U does nothing to affect length, angles, and orthogonality. That's really cool. Let's prove it here. We're going to consider the square, ux. So we're going to consider the length of u times x squared. Well, this is a vector, right? How do we write the magnitude squared? That's just ux times ux, right? How did we write this dot product? It was ux transpose times ux. How do we do a transpose? Right? The order flops and everything gets a transpose, right? So it's x transpose u transpose times ux. Well, what's u transpose times u if we have orthonormal columns? It's just x transpose times the identity times x. And this is x dot x, which is the magnitude of x squared. And taking square roots on both sides finishes that problem. How do we prove part 2? For part 2, how do we rewrite this? The same trick here. Once you see dot product, you do transpose stuff. So for part 2, we look at ux dot uy. And we write this as y transpose times u transpose times u times x, which is y transpose times x, which is x dot y. Yeah, and there's a similar trick for part 3 here of this theorem. Alright guys, so I think that that's all that I have to tell you in this video. I hope that you found it entertaining, because I think this stuff's kind of beautiful. If you have any questions whatsoever, please reach out to me via email, and I'm happy to help in any way that I can, or we can schedule a time to Zoom. Thanks so much for watching. I'll see you in the next video.